Great. Let's get back to it then. Last time we were talking about DFAs. And in particular, unfortunately, I had to sort of stop in the middle of an interesting example. This is a DFA for binary numbers. And the idea is it accepts if some binary number x is divisible by 3. And it rejects otherwise. And as I mentioned last time, this is a problem which is not easy to do like for ordinary people. Like if I just show you a binary number like that, is that number divisible by 3 or not? The answer is, I don't know. I mean, I don't even know what number that is, like what number in base 10 that represents. Probably if I had to answer this question, I would convert this to a base 10 number and then decide if that was divisible by 3. But actually, you can make a DFA which answers this question for you, and it's not even so hard to do. So as I started off last time, this DFA is going to have 3 states depending on the remainder when you divide this number by 3. That's what the mod business means. When you divide by 3 and look at the remainder, it could either be 0, 1, or 2. So this is going to be the setup of my DFA. And we want to start, when you start reading the number, you start with essentially 0. The empty string would represent the number 0, which is 0 mod 3. And this should be the accepting state because that's how this thing is supposed to work. It should be accepting if the number is divisible by 3. All right? And the basic idea, so what we have to do is fill in the arrows. Every symbol that you read is either a 1 or a 0. And you have to think about when you read a new digit of this number, a new bit, as they say, how does that affect the value of the number that you're talking about? And what we said last time is if I'm reading some number x and I see a 0, since you're reading left to right, so I'm imagining, say, you read, let's say these first, off the top, let's say you read these first 5 characters, and that represents some number, and then you tack another 0 onto the end of it. The effect of that is to multiply this number by 2. That's because this is how the binary system works. When you tack a 0 onto the end of a number, it has the effect of multiplying by 2. Just like in base 10, if you put a 0 on the end, it multiplies by 10. So if I'm reading x and I see 0, it becomes 2x. And if I'm reading some number x and I see a 1, it becomes 2x plus 1. That's what we said last time. And this is the basic idea which will allow you to decide where all of these various arrows ought to go. So here is, let's say I am in the x equals 0 mod 3 state. And the arrow for 0. So if x equals 0 mod 3, that means that x is a multiple of 3. So I can write x equals 3k. And then ask myself, what about 2x? Because when you read a 0, it changes this into 2x. So that means 2x is 2 times 3k, which is still a multiple of 3, right? That's 3 times 2k. And this is still 0 mod 3. That means on my diagram, the 0 arrow does that. So if you have a number that's already divisible by 3 and you read a 0 on the end of it, that multiplies the number by 2, but it's still going to be divisible by 3 anyway. All right? I think this is where we ended last time. Let's try the arrow for the 1. So in this case, we still have x equals 3k. Sorry. But this time when I read a 1, it becomes 2x plus 1, right? That's the second thing that I said here. When you read a 1, the number changes to 2x plus 1. And what does that mean? Well, this now, plugging in again, x equals 3k, this will say 2 times 3k plus 1. What is that in terms of a multiple of 3? You want to know, is it equal to a multiple of 3 or a multiple of 3 plus 1 or a multiple of 3 plus 2? Well, I can rearrange this ever so slightly to say that. And now you say that is 1 more than a multiple of 3, right? It's 3 times something plus an extra 1. So this is 1 mod 3. And that means on my diagram, the 1 goes like that. All right. Can we try the arrows from the middle state? I hope everybody's following this just a little simple, arithmetic kind of a stuff. Let's look at the x equals 1 mod 3 state. All right. Again, I need 2 arrows. In this case, we start by saying x is 3k plus 1. That's what it means to say x is 1 mod 3. And then think about what happens when I do the arrow for 0. It turns into 2x, which is 2 times 3k plus 1. Make sure you put those parentheses in there. I know there are some parentheses haters out there, but it really matters in this in an example like this. We should distribute the 2. I'm trying to simplify this to see what the leftover bit is. Distribute the 2, it becomes, well, I guess 2 times 3k plus 2. Can anyone say, what is this mod 3? It is 2, yeah. He gave me the gang sign. 2. This is 2 more than a multiple of 3. So this is 2 mod 3. What does that mean? It means the arrow going from the middle state, labeled with a 0, goes to the end, like that. Right? How about from the middle state, labeled with a 1? For a 1, this turns the number, remember, into 2x plus 1. That means 2 times I had a feeling I could just wait a few seconds and it would all be better. Like so, right? This is 2x plus 1. And then, rearrange or simplify or whatever. I want to see, is this a multiple of 3? Is it 1 more or is it 2 more? So if I distribute the 2 again, that's 6k plus 2 plus 1. 6k plus 3. Is that a multiple of 3 or 1 more or 2 more? I say that is a multiple of 3, right? You could factor 3 out of this. It's 3 times something, right? 2k plus 1, I guess. All right, anyway, that is 0 mod 3 because it equals a multiple of 3. So the arrow here with a 1 goes back that way. All right? Can I can I have you guys see, can you fill in, there should be 2 arrows here. I hope that you're following what I've done here. You should do basically the same thing again, but for the x equals 2 mod 3 case. So start by saying x in this case is 3k plus 2, and then see what happens when you multiply by 2 or do 2x plus 1. I'll give you a moment to see what you think. I'm going to write down the little arithmetic here. All right, let's talk about these. These are, this is what I got when I worked out the arithmetic. So for the 0 arrow, if x is 3k plus 2, then 2x is like that. 2 times 3k plus 2, distributing the 2 gives me this. And now this is equal to 1 when I go mod 3. That's because mod 3 is like removing all multiples of 3. So this will go away entirely when I go mod 3, and then 4 is the same as 1 mod 3. And so I get 1 mod 3. What that means is the arrow from this state labeled with a 0 goes back to the 1 state. So it's like so. If I'm 2 mod 3 and I put a 0, it goes back to 1 mod 3. All right, and then this business here, so doing a similar thing, it's just 2x plus 1 instead. You get down to 6k plus 5. When you go mod 3 there, the multiple of 6 goes away entirely because that's a multiple of 3. And then what's left over is 5. But 5 is equal to 2 mod 3. And so this is 2. So that means if you're in the 2 state and you see a 1, you stay in the 2 state. So it's like this. I don't know what's up with that. Everything's fine. All right. So this is sort of my final answer. This, in my opinion, is really pretty interesting. Just the fact that this exists and is so simple to do, it means that, you know, like when I said before, like that number right here, I don't know if this is divisible by 3 or not. Actually, if you know what this diagram is, we can just read this one letter at a time and see where we end up. So I'm going to do that. We start here, right? And I'm just going to follow the arrows, reading that binary number from left to right. It says 1, 0, 1, 1, 1, 0, 1, 0, 1, 1, 0. I think it is divisible by 3. Did I do that right? I'm looking back and forth. It's hard to tell, but I think it actually ends up back here. So apparently, I still don't know what number that is, but it seems like it is divisible by 3. Strange but true. Right? I think that's kind of cute. I mean, I can lie to you and say this is actually a useful diagram. I don't know how useful it is to tell if a binary number is divisible by 3 or not, but in my opinion, this is actually a far better way than trying to convert that number to base 10 and then using some base 10 divisibility test, right? If for some reason you had this diagram memorized or something, you could very easily tell if any binary number is divisible by 3. Which I think is kind of cute. All right. There are similar, would you believe me? I don't think we need to work it out, but you could do this really for binary numbers being divisible by 4 or 5 or whatever. You could make a similar diagram like this. It would be slightly more complicated, but it would work out in the same way. All right. So the moral of the story is DFAs, they are kind of primitive, but they actually can do interesting and useful kinds of computations, even ones which, at least on a surface level, would seem to be hard to do by a human being, such as this one right here. All right. Excellent. Great. Let's talk a little bit, for the rest of today, I want to talk a little bit more kind of theoretical, or somehow, not like super theoretical, but most of the questions on the homework are, well, a lot of the questions on the homework are about sort of like, here's a set of strings, and I want you to make a DFA which accepts these kinds of strings and rejects these kinds of strings. We can also go the other way around. So how about, here is a DFA. You tell me what are the strings that it accepts. And this is a simple example, but let's talk about A's and B's again. There's a DFA. This one has two accepting states, which is allowed. It can have as many accepting states as you want. My question here is kind of the maybe converse type question to what we usually say. I show you the DFA and then say, what are the strings which are accepted or not? And maybe, you could, if you don't have any way of telling, you could just sort of write down a few strings if you like and try to sort of see a pattern. Which strings are accepted? Something like A or B or AB or BA or AAB. I'm just writing some random strings down here. Can we just see? And each one you can test by doing the arrows. So just A by itself, you start here and you go A, and it stops in the accepting state. So just A by itself is accepted, right? B by itself, is that accepted or not? I think it is. You start on the left and then you move to the middle and then you stop, and it is accepted. How about A followed by B? That is, you go A, B, and that is accepted. So this one is accepted. BA. There you go, BA, that is not accepted. So this one is rejected. AAB, I think that is accepted. AAB, like that, that is accepted. ABB, it seems to me that is also accepted, right? It goes ABB, so that's accepted. ABA, ABA, that's rejected, right? Etc. Anybody have a feel for this? Can you say in general what are the strings that are accepted?
If an A follows a B, it's rejected.
If there's an A after a B, it's rejected.
After any B.
Yes. Yeah, I think I agree. Can really, if there's ever an A after a B, it's rejected. Yes. I would like to, this is a fine answer. Is it possible to phrase that in terms of which strings are accepted rather than which strings are rejected? Yeah?
Strings that don't have any A's after B.
All right. This is like the opposite of what he said. Strings that don't have any A's after any B's. Can anyone describe maybe in a different way that's a little more affirmative without using the word don't or something?
A to the N, B to the N.
A. Yeah, this is a much more convenient for our purposes way of writing this. This accepts any string of the form A to the N, B to the M. Is that what you said? I think I agree with this. It can have any number of A's first, followed by some B's, but that's it. You cannot put more A's after the B's, which is what these folks said before. But this is a little more, I don't know, a little, for our purposes, this is typically the way that is going to be best to say the answer to a question like this. Which are the strings which are accepted? It's any string of the form A to the N, B to the M. And remember, just when we write this, N and M could be 0, right? Where if N, for instance, if N is 0, A to the 0, that would mean you just don't have this part at all, and it's just a bunch of B's. But that still is accepted. And the B part could also be 0, right? Excellent. And of course, the N and the M are not necessarily equal to one another. This is different from if you said A to the N, B to the N. If you use the same letter in the exponent both times, this is not the same then. That would mean the number of A's has to equal the number of B's, which this machine does not require that. All right? So the way that we say this formally speaking, let's call this DFA let's sort of give it a name as a variable, right? Call it M. So this is M. M is this DFA, right? We say the technical language here, we say the language accepted by M is this as a set, A to the N, B to the M. All right, this is how we're going to write this. Remember from the first day we had just sort of basic terminology. The word language, remember, just refers to any set of strings. And so this set that I wrote there, it certainly is a language, and it's called the language accepted by M. So generally speaking, maybe I'll write this as a little def here. If M is a DFA, then the language accepted by M, or sometimes we just say the language of M, the language, the language accepted by M is the set of all strings. I mean, it is the set of all strings accepted by M. And we write it L of M, the language of M. All right? So every DFA has a language, L of M, the language accepted by that DFA. All right? And here's a bit of terminology that will be very important. I mean, we're going to use this terminology all the time. Any language, remember the word language just means any set of strings. So you could imagine there are many, many different languages that could be the language of something or other. For any set, or I'll just say language, that means the same thing. For any language L, we say L is regular, a regular language when there is some DFA M such that L is the language of M. All right? That's what it means to be a regular language. So a regular language is one which is the language accepted by some DFA. Right? And so when we talk about sort of, as you know, I'm trying to get back to the kind of introduction to this course that I gave. I said this course is all about the capabilities of different types of machines, right? So when we ask question about sort of what kinds of computations can a DFA do? Questions about what kinds of computation can DFAs do? These are actually equivalent, these kinds of questions. You could just rephrase the same questions, equivalent to which languages are regular? Because regular means it is the language that is accepted by a DFA. So if you ask me, what kinds of things can a DFA do? That's really the same question as asking me, what kinds of languages are regular languages? And so this is something I mentioned maybe on the first day. You could phrase everything in this class in terms of machines, or you could say this class is all about machines, or it is completely equivalent. You could phrase everything in terms of languages and say this class is all about languages. And that's why like our book is called Formal Languages or something like that. The title of the book doesn't mention machines or computation at all. It's because from the point of view of the book, They are taking this sort of language as the fundamental thing to talk about. Although, of course, all of these machines are in the book. They're just saying the book is about languages. You could just as easily say the book is about machines. All right? So DFAs and regular languages kind of go together. A regular language just means it is the language which can be accepted by some DFA. All right? And of course, the big question, overarching question that we're going to be talking about, over many weeks, the big question, I asked this big question last time, but I phrased it differently. Last time I said the big question is, what kinds of things can a DFA compute? But that is actually the same as saying, which languages are regular? That's the same question that I just wrote there. Maybe I don't need to write this again, but I'm going to write it again. Which languages are regular, right? For example, how about something like this? Here's a language. We are usually going to write languages as sets like this. So I hope you remember from your discrete math days how to write and read set theory notation. We're going to do this all the time in this class. A to the n such that n is even. Is it regular or not? The question is the same as saying, is it possible to make a DFA that accepts only when the power there is even? And the answer is yes. This is a DFA. This is like the first example that we ever saw of a DFA. It's this kind of thing, right? This is a DFA which accepts that language. And so the answer here is this is regular because there is a DFA which accepts that language. And that's it. I just wrote it for you. All right? A to the n such that n is even. Or something like a to the n, b to the m, where n and m are natural numbers. Is that regular? Yes, it is. That's the example that we just did like a few minutes ago. We have a DFA whose language is that. So this one also is regular. Right? How can you tell just by looking at a language if it's regular or not? The answer is that it's complicated. There's not like a very straightforward way to just look at a language and tell if it's regular or not. Although this too is something that we're eventually going to get to. Something like I mentioned last time, or sometime, I don't know. A to the n such that n is a prime number. This actually turns out to not be regular. This is not regular. It is not possible to use a DFA to check for prime numbers. I mean, it's hard to give a rigorous proof of this, but basically the idea that I have in mind at least is to show something is prime, you in theory would have to divide it by all other numbers, but no DFA can do that because a DFA is only finitely many states and is not able to handle all possible divisors. Another thing which is not regular, it turns out that, a to the n times b to the n, where n is a natural number, this is also not regular. And I will just point out, what's the difference between this here and this one? A to the n, b to the m. This means just some number of a's followed by any number of b's. This one here means some number of a's followed by the same number of b's. And it turns out that is enough to screw with the DFA. Like a DFA is actually not capable of making that kind of calculation about do I see the same number of a's as b's? What's going on with these screens? All right. So, and I will just say, to show something is regular is fairly easy. You just have to demonstrate a DFA. To show L is regular, just demonstrate a DFA which accepts L. This is typically not so hard to do. To show that a language is not regular is much, much harder. And this is something that we're going to get to eventually, but I will just point it out at this point. To show that L is not regular, you have to do the opposite, which means you have to somehow prove that no possible DFA can accept L. And that's much harder because you have to somehow consider all possible DFAs and demonstrate that none of them could ever generate this language L. So to show L is not regular, you must prove that no DFA accepts L. And that's much harder. Because your proof needs to somehow consider all possible DFAs and demonstrate that none of them can accept this language that you're talking about. That is a lot harder to do. All right. What I want to talk about for the remaining bit of time that we have is something that I didn't actually get to. I don't know if anybody noticed. The definition of a DFA. There are a few details that I never really said specifically as far as what exactly counts in a DFA and what exactly is allowed in a DFA. One thing that ought to be, like from an abstract mathematical point of view, ought to be kind of a red flag is that when I started talking about DFAs, I just said something like, you know, a DFA is like this, and I started drawing stuff right away. This was the first example. It's like that. Everybody was very polite when I said this, and I didn't sense that any of you thought that it was inappropriate for me to say this. But in a sense, this is a totally bogus definition. To treat this like a real definition, there are many objections that you could have made. Like, for instance, a DFA is really just like a picture of something. That's what a DFA is. For example, you may have noticed, like here, this is one circle, right? But it's not even a circle. It's like it's got like these little hairs on the top. Is that part of a DFA? The little hairs? No, it's not. Like this is really what if someone started asking me questions like this, I would say, okay, no. This is a picture of the DFA, right? This particular drawing is not what the DFA is. This is a representation of the DFA, okay? I hope that everybody agrees with me. But then, of course, the question is, okay, then what is it really? If this is just a picture of it, this is just a representation of it, then what is the true nature of the DFA, right? This sounds like sort of a stoner type question, like, yeah, man, like what really is it, man? Like all you know is like the representation of it like on paper, but that's not really what it is, man. Like what is it really? What is it is, man? This is what I want to talk about for the remaining 16 minutes. What really is a DFA? It's not that. Because, this sounds like just sort of a silly question to ask maybe, but there are real questions behind this. For instance, I said several times, like every state in the DFA is required to have outgoing arrows for every letter, but I never really said that as part of any definition. I would like to have a real definition which includes all the rules like that. And maybe there are some other rules that I didn't even tell you about yet. So we would like to talk about a real definition. And if you ask me, okay, this is a picture of the DFA, what is it really? We have to ask ourselves sort of what is the important information that is being encapsulated in this picture. What is the important information about the DFA? This picture is a depiction of the DFA, but what are the things that we are depicting? Well, I would say, first of all, there's the states, right? In this DFA, there are 2 states. I drew them like circles, but of course, if you want to, you can draw them however you like, but they are the states. Can anybody say what else in the diagram is important? There's a few other important ingredients, yeah.
Where it starts.
Okay, there is a designation of the starting state. Great. What else? Yeah? The transitions, yeah, those are the arrows. What else? There's one other thing that the diagram indicates.
The accepting and rejecting states.
Right. I will just say the accepting states. Although, I mean, there are rejecting states also, but we just consider everything that's not accepting is automatically called rejecting. The accepting states. Remember, there can be more than one. In this example, there's only one. All right? These are the important information about the DFA. I will just say one more thing that is kind of implicit in these other ones. Maybe I'll put this in parentheses. The alphabet. Like when you look at this DFA, the alphabet is just A. But some other DFAs, their alphabets are A's and B's and whatever. All right? There are 5 ingredients which makes up a DFA. And so the technical definition of a DFA is just a list of these 5 things. That's it. So here is the formal definition of a DFA. All right, a DFA consists of those 5 ingredients. I'm not going to write them in that same order because there's a standard order. You guys were just shouting them out in any old order. So this, you could say, is the true definition of a DFA. It's a collection of those 5 bits of ingredients. The way that we typically would write that in set theory is a 5-tuple, because they go in a particular standard order. I'm going to write it this way. M equals Q. This is standard notations, and I will tell you one by one what each of these things mean. Q, sigma, delta, Q naught, and F. Where, I'll tell you what each of these things are. Q is a finite set. This is called the set of states. So in my example, there were 2 states. We think of them as like little circles in a diagram, but that's not what they are. What they are is just there's 2 different states, that's all. All right? The sigma refers to the alphabet. This is also has to be a finite set. This is the alphabet. You know, in our examples, it's usually like A, comma, B. That's the typical alphabet that we use, but it could be anything, of course. Delta. All right, here's where it gets a little complicated. Delta is what describes the transitions. Those are the arrows in the diagram. And there are various ways that you could describe what delta is. But you have to describe everything here in the language of set theory. So you could say delta is a set, or maybe it's a tuple. It's actually most convenient to describe it as a function. And just like we do in discrete math, I'm going to tell you the domain and the codomain of this function. This is complicated, but I'll dissect this in a moment. Its domain is Q cross sigma. That cross is the Cartesian product of sets, which I hope you remember. Although if you don't, I'll refresh our memory. And then the codomain is Q. So this is called the transition function. This is a function which describes what the arrows look like. All right, continuing on the list, the Q0. Q0 is the starting state, and this is simply an element of Q, right? Q is the set of all the states. Q0 is just one of those states which is chosen to be the starting state. This is the starting state. And F is the set of accepting states. So to say what exactly F is, it is any subset of Q, right? Q is a set of all the states. F is just some of them. It is a subset of Q. So this is the set of accepting states. That is the formal, we call this the formal definition of a DFA. So if you are, in casual situations in the club, say, trying to describe a DFA to somebody else, your favorite DFA, you should never describe it in this way. You should get a napkin and draw the picture, all right? But the picture, your fine friend will say, that's not really the DFA, is it? No. The true nature of the DFA is just this. It's some abstract collection of sets and functions and whatever, all right? Let's just try one example just to clarify what all of this business is supposed to mean. I will draw the picture of a DFA, and then let's try to write down its corresponding abstract sort of formal object. So, for example, how about that same DFA that I was talking about a few moments ago? This one. Now, I'm going to give names to these states. I'll call them S1, S2, S3. And the arrows went like this. Sorry, no B here, like that. I wrote a B there, but it's just a. Okay, so this diagram, you'll have like homework problems like this. It's just very easy if you know what you're doing. Let's write the formal description of this DFA. All right, this is always easy to do if you know what's up. The formal description is, now I'm just going to write it all, M equals, maybe I'll just write these things here, and then I'll tell you down below what each of those things is. So it is M equals this tuple, where you just have to say what are each of those ingredients. So Q is the set of states, and in this problem there are 3 states. And they are S1, S2, S3. All right? So that's what Q is. Make sure you should technically be distinguishing between the curly brackets and the roundy parentheses. These parentheses are a 5 tuple, meaning that this order is important. This is a set, meaning that it should have no repeated elements and the order doesn't matter. Okay, what about sigma? Sigma, you can tell, is the alphabet, which is AB in this example. All right. Now, delta, the transition function, is actually the most complicated ingredient, so maybe we could say what the others are first. Q0. Can anybody say what is Q0 in this example? Q0 is meant to be just a certain element of the set Q. Yeah? It is S1. Yeah, that's what on the diagram, you can see that's the starting state. So that's S1. And F, the set of accepting states, what do you say? First of all, it is a set, so. Okay, yeah? S1 and S2. Yeah, great. All right. I don't know about you. I tend to draw my left-hand set thing. It looks nicer than my one on the right. I got to work on that maybe. Okay. And what about the delta? And this is the most complicated ingredient. Again, it's not hard to do. It's just you have to sort of know what to do when you write it down. And delta, what makes it hard to write down what delta is it's a function. Now, typically a function, in a typical math class, a function you write using equations, f of x equals cosine of x or something. But actually this is not a function which you can describe by a formula. Like, it's not a cosine or of anything or anything like that. The only way to write down what delta is you just have to write out all the possible values of delta. And the way that we write them is like this. For example, the first value of delta is, what is delta of S1 and A? And the meaning of this is, delta is supposed to represent, if I'm in this state and I see this letter, what state do I go to next? And the answer is S1 in this case. So this arrow right here corresponds to this one particular value of the transition function, delta. And the meaning of this, delta, you plug in a pair, a state followed by a letter, and the answer that you get out is a state. And it is, wherever the arrow goes, that's what you get. So my next, how many total values are there? I think there's going to be 6 total values. I have to write down delta of S1 and B is something. Also delta of S2 and A, delta of S2 and B, delta of S3 and A. Sorry, I'm running out of space here. Delta of S3 and B. If we can write all of those, that will be the full description of this function delta. So delta of S1 and B means when I'm in state 1 and I see B, I go to state 2. So that is S2. Delta of S2A means I'm in state 2, I see A, I go to S3. So this is S3. Delta of S2B means I'm here, I see B, I go back to S2. So that's like that. Delta of S3A means I'm here and I see A, I end up at S3. And delta of S3B is also S3. So this is the complete description of the transitions. And you can see just, every arrow on the diagram corresponds exactly to one of these 6 things. And this is the abstract way in which we represent the arrows. They are represented by a function called the transition function. All right? If I show you any DFA diagram, it is always easy to just write down all of this stuff. I mean, it takes up some space, I suppose, but there's nothing hard about doing it. Can I just go back to this right here? Just a little sort of set theory review, perhaps, just about how this is written. Can we make sense about this? Remember what this means. This right here is the domain. That is to say, those are the things that you plug into delta. And so the domain here, what is the, anybody remember from your discrete math class, what's the meaning of this product here? If I have 2 sets, what does it mean when I write the product? If I have, say, A and B, what is A cross B? Usually we say cross for this. I hope you recall. Remember?
Cartesian product?
Yes, it is the Cartesian product. Yeah, do you remember what that means? Yeah?
Every element of Q is put together with every element of
Yeah.
the alphabet.
Yeah, so this is, when you take the product of 2 sets, the result is the set of all pairs, something comma something, where the first thing is in the first set and the second thing in the second set. So here, when I wrote this a few minutes ago, what I meant was the domain of this function is pairs like, a state, comma, a alphabet letter, right? That's the domain, and you can see in the example that we did, that is the kind of thing that you plug into the delta, all right? So when I wrote this before, really I was telling you what is the kind of thing that goes into the delta, and then this is what is the kind of thing that comes out. That's called the codomain. So the codomain, which is to say, this is the set of answers, is individual states, right? The codomain is the set of Q, and Q is the set of states. So the codomain is individual states. So when you write this, what it's doing is telling you what are the kinds of things that you plug into this function, and then what are the kinds of things that you get out. The answer is what you plug in is a pair, a state, comma, a letter, and what you get out is a state, just like I wrote up here. All right, but this delta can be any function. We don't, in a calculus class, you're used to saying it has to be continuous or whatever. There's no such thing as continuous, though. This is just a function of abstract sets, and it has only 6 values in that example. All right, would you believe me if I said you could go the other way too? So if I show you the diagram, it's fairly easy to write this description, and the other way around is also true. If I show you a description like this, you can easily write down the diagram that corresponds to the abstract description. Maybe we'll do an example like that next time. I think that'll do for today.